They claim the James Webb Space Telescope spotted a large object about 10 light years away moving toward Earth.
Is life as we know it unique to our planet? Or is there some other distant planet or moon out there, just out of our sight, that hosts extraterrestrial beings, even if only at a microbial level? Well, as it so happens, Proxima Centauri, the closest star system to our own, has long fueled imaginations with its mysterious Earth-like planet, Proxima B. As scientists turn the James Webb Space Telescope toward this tantalizing celestial neighbor, their discoveries paint a vivid yet troubling picture. NASA has warned us now that the James Webb Telescope has finally shown us what's happening on Proxima B, and it's a total nightmare. So what is it that we have learned, and how does it affect us all? Well, let's find out as we explore the latest frontiers of space exploration. Proxima B, the planet that could be the second Earth. A mere 4.2 light-years away in the Proxima Centauri star system, Proxima B is the closest confirmed planetary neighbor to our solar system. Orbiting a dim red dwarf star, Proxima B resides within its star's habitable zone. This positioning alone makes Proxima B a compelling candidate for further exploration. However, unlike Earth, the planet is tidally locked, meaning one side perpetually faces its parent star, basking in unending daylight, while the other remains in eternal darkness. This stark division creates extreme environmental conditions, with one hemisphere potentially searing under constant sunlight and the other freezing in shadow. However, the narrow strip along the Terminator line, where day transitions into night, offers a potential haven for habitability. This is where life may reside. So, what makes Proxima B so important? Why is life only confined to Earth so far? And if the planet can host life, will we be able to colonize it one day? Let's get to it. For any advanced alien life, even at a microbial level, to thrive on Proxima B, adaptation to the planet's extreme conditions would be essential. Proxima B's proximity to a red dwarf star brings additional complications. Red dwarfs are known for their volatile stellar flares, emitting intense radiation that could strip away a planet's atmosphere or sterilize its surface. So, does the planet still retain enough of its original gaseous envelope to support life? Well, we can't be 100% sure at this point. However, Proxima B still represents a tantalizing glimpse into the possibilities of life beyond our planet. Its unique conditions challenge our understanding of habitability and push the boundaries of what life could endure. What have the James Webb Telescope and other observatories revealed? With its advanced observational capabilities, the James Webb Space Telescope has provided us with unprecedented insights into the deepest recesses of the cosmos. It has significantly advanced our understanding of exoplanets, particularly those that may harbor conditions suitable for life. Through its sophisticated instruments, JWST has provided detailed observations of several exoplanets, such as the K2-18b, a sub-Neptune exoplanet located approximately 124 light-years away. The planet hosts methane and carbon dioxide in its atmosphere. These findings suggest that K2-18b could possess a hydrogen-rich atmosphere with a water ocean beneath, aligning with the characteristics of a Hycean world, a type of planet with potential habitability beneath a thick atmosphere. Similarly, LHS 1140b, a super-Earth exoplanet situated about 50 light-years away in the constellation Cetus, may be a rocky or watery world with a substantial atmosphere, possibly rich in nitrogen. Its location within the habitable zone of its red dwarf star suggests that it could support liquid water on its surface. The JWST has also examined the TRAPPIST-1 system, which contains several Earth-sized exoplanets within the habitable zone. However, observations have revealed that the system's star exhibits significant stellar activity, which could impact the habitability of its planets by affecting their atmospheres and surface conditions. While these findings are promising, it's important to note that the detection of molecules like methane and carbon dioxide does not confirm the presence of life. These compounds can be produced through both biological and abiotic processes. Therefore, further observations and analyses are necessary to determine the true nature of these exoplanets. When it comes to Proxima B, the story is a bit complicated, but promising nonetheless. The High-Accuracy Radial Velocity Planet Searcher, or HARPS, mounted on the European Southern Observatory's 3.6-meter telescope in Chile, played a pivotal role in the discovery of Proxima Centauri B in 2016. Using the radial velocity method, HARPS detected subtle wobbles in the star's motion caused by the gravitational pull of its orbiting planet. The Atacama Large Millimeter-Submillimeter Array, or ALMA, consisting of 66 precision antennas in Chile's Atacama Desert, expanded our understanding of the Proxima system by investigating its potential dust and debris disk. Such structures often indicate ongoing planet formation and could harbor additional planets. The Hubble Space Telescope, or HST, the predecessor to the JWST, contributed by observing Proxima Centauri's ultraviolet and optical emissions, providing critical insights into its stellar activity. As a flare star, Proxima Centauri frequently emits powerful solar flares that can strip planetary atmospheres, posing challenges to habitability. Hubble's data has helped scientists evaluate the environmental stresses that Proxima Centauri B might face, offering a clearer picture of its potential for life. Further refinement of our understanding of Proxima Centauri B came from the European Southern Observatory's Very Large Telescope, or VLT, at Paranal Observatory. Its espresso spectrograph improved measurements of the planet's mass and orbit, and, in 2022, identified Proxima Centauri D, a possible third planet in the system. The Chandra X-ray Observatory has also provided valuable observations of Proxima Centauri in the X-ray spectrum. By analyzing high-energy emissions, Chandra has illuminated the star's impact on the atmospheres and magnetic fields of its planets. Similarly, NASA's Transiting Exoplanet Survey Satellite, or TESS, has monitored Proxima Centauri for brightness variations caused by stellar activity. Beyond planetary exploration, the Gaia Space Observatory has revolutionized our understanding of Proxima Centauri's position and motion within the Milky Way. Now we know that the star is 4.2 light-years from Earth. Gaia's data revealed Proxima's rapid proper motion of 3.85 arc-seconds per year and its complex trajectory, suggesting it may have been gravitationally captured by the Alpha Centauri system, rather than forming alongside it. Additionally, Gaia's mapping of the local stellar neighborhood has contextualized Proxima Centauri within the broader galactic framework, while its precise astrometric data has refined models of its known planets and highlighted the potential for undiscovered companions, setting the stage for future exploration. Future observations promise even more groundbreaking discoveries. The James Webb Space Telescope is poised to analyze the atmospheric composition of Proxima Centauri B, potentially detecting biosignatures or conditions conducive to life. Meanwhile, the extremely large telescope is expected to directly image exoplanets and study their atmospheres with unprecedented detail. Together, these instruments have transformed Proxima Centauri from a distant point of light into a richly characterized star system. Their collective findings form a foundation for future exploration, offering tantalizing glimpses into the potential for life beyond our solar system and deepening our connection to the cosmic frontier. So, what can we make out of all this data? Is Proxima B home to life as we know it? Hostile environment and astrobiological possibilities? The question of whether Proxima B can host life or not is perhaps the most interesting aspect of the planet, because the ground realities are fairly paradoxical. On the one side, Proxima B presents one of the most challenging environments for potential life, and at the same time, the planet is situated within the habitable zone of its planet and may also contain the ingredients for organic life. So, what's the challenge? Proxima B is bombarded with intense radiation, primarily due to Proxima Centauri's highly active nature as a red dwarf star. These stars are smaller and cooler than our Sun, but make up for this with their extreme volatility. Proxima Centauri emits flares that are 10 to 100 times more energetic than those of our Sun. These flares occur multiple times a day, releasing high-energy particles and radiation across the ultraviolet, X-ray and gamma-ray spectrums. If Proxima B ever had a thick atmosphere, constant bombardment by such flares could strip it away over millions of years. This atmospheric erosion would expose the surface to unfiltered radiation, making it hostile to most known forms of life. Even if Proxima B possesses an Earth-like atmosphere, the radiation could destroy its ozone layer, leaving the planet's surface unprotected. Moreover, the influx of charged particles could produce powerful auroras across the planet, visible even on the night side. These auroras, while visually stunning, might disrupt any potential electronic or biological systems reliant on stability. If life exists on Proxima B, it must be uniquely adapted to survive under these extreme conditions. But it is not as impossible as one might initially think. For example, extremophiles like Deinococcus radiodurans are capable of surviving extreme radiation levels by repairing DNA damage rapidly. Life on Proxima B could evolve similar mechanisms, with efficient cellular repair systems or redundant genetic encoding to withstand constant radiation. Moreover, back on Earth, fungi such as Cryptococcus neoformans thrive in high radiation environments like the Chernobyl nuclear reactor, using melanin to convert gamma radiation into usable energy. To avoid direct exposure to radiation, life forms, if there are any on Proxima B, might exist beneath the planet's surface. Subterranean habitats could provide natural protection, with organisms relying on geothermal heat or chemical energy for sustenance. Similar to Earth's deep-sea hydrothermal vent ecosystems, life on Proxima B might thrive in extreme conditions, relying on chemosynthesis rather than photosynthesis. Plus, if Proxima B has ice-covered oceans, as some models suggest, life could exist in subsurface liquid water pockets, insulated from radiation by a thick ice shell. There is no shortage of examples when it comes to highly resilient life forms, as we have countless such organisms even on Earth. For example, in our planet's volcanic regions, some microbes use sulfur instead of oxygen for metabolism. This could also be the case with Proxima B. Moreover, to withstand surface radiation, life forms might evolve dense, reflective exoskeletons or biofilms capable of deflecting or absorbing harmful rays. Organisms could also develop specialized pigments that convert harmful radiation into energy, similar to photosynthesis, but adapted for high-energy wavelengths. But this sounds more like a nightmarish hellscape rather than a habitable planet. How would we send manned missions to or colonize this distant second Earth? Well, that's where things get interesting. Future colonization of Proxima B. If humans were to colonize Proxima B, the process would likely unfold over several centuries, starting with advanced robotic missions in the mid-21st century. These missions would map its surface, assess its atmosphere, if any exists, and study its climate and geology in detail. Following this, we could deploy more complex autonomous technologies to begin terraforming efforts or create artificial habitats capable of withstanding the planet's harsh conditions. By the 22nd century, assuming advancements in propulsion systems such as nuclear fusion or breakthrough methods like warp drives, interstellar travel might reduce the journey to Proxima B to mere decades. Human settlement would follow only after reliable life support systems and sustainable energy sources have been developed. If everything goes well, a self-sustaining colony might emerge by the 2300s. This kind of optimism is rare nowadays, but a couple of decades back, that's what everyone was thinking. In the 1960s, optimism about space exploration was at its peak, fueled by the space race between the United States and the Soviet Union. Cultural milestones, like 2001, A Space Odyssey, reflected a belief in boundless progress, imagining fully automated interplanetary travel, space stations as hubs of human activity, and moon bases as stepping stones to the stars. This optimism was driven by breakthroughs such as landing humans on the moon within a decade of the first artificial satellite launch, as well as the exponential growth of computing power, materials science, and propulsion technology. While the space fever is now over, the practical need for spreading our species persists. Colonizing other planets is a necessity for the long-term survival of humanity. Earth faces existential risks, including climate change, overpopulation, asteroid impacts, and even the eventual exhaustion of its natural resources. Expanding beyond Earth would diversify humanity's survival chances, ensuring that no single catastrophe could extinguish our species. As the closest exoplanet located within its star's habitable zone, Proxima B offers a tantalizing possibility for sustaining life. Despite challenges like its exposure to intense radiation from Proxima Centauri and its potential tidal locking, its Earth-like mass and possible water reservoirs make it a prime candidate for future exploration. If proven to have an atmosphere or subsurface ocean, Proxima B could become a second home for our species. Proxima B is also important because it provides an opportunity to test our capabilities in adapting to alien environments. By colonizing such planets, we could pioneer technologies to harness energy, grow food, and sustain ecosystems in extreme conditions. These innovations might also have applications back on Earth, improving sustainability in the face of growing global challenges. Moreover, the discovery of life, even at a microbial level, on Proxima B or elsewhere, would be a groundbreaking milestone in human history. It would confirm that life is not unique to Earth and might fundamentally change our understanding of biology, evolution, and the universe's potential for harboring intelligent civilizations. Establishing contact with alien microbes could inform us about alternative biochemical pathways and novel adaptations to extreme conditions, and perhaps even provide insights into the origins of life itself. Proxima B's unique tidal locking, where one hemisphere perpetually faces its star while the other remains in eternal darkness, offers distinct challenges and opportunities for energy management. The perpetual day side, exposed to constant stellar radiation, could be a powerhouse for solar energy collection. Advanced solar panels, optimized for the specific wavelength emissions of Proxima Centauri, which includes a higher proportion of infrared and low-energy light, could convert this energy into electricity efficiently. These panels would likely need to be engineered with radiation shielding to withstand stellar flares. This energy could be stored in high-capacity batteries or transferred to the dark side using superconducting cables. These cables, operating with near-zero energy loss, would enable the transfer of energy across the planet's surface or through subsurface tunnels. On the dark side, where temperatures would plummet due to the lack of stellar radiation, geothermal energy could serve as a viable alternative. The planet's core, if sufficiently active, could provide heat that is harnessed through geothermal systems to power settlements and maintain life support. Artificial lighting systems powered by energy from the day side could mimic natural sunlight, supporting photosynthesis in agricultural areas and ensuring human circadian rhythms are maintained. The concept of energy balance between hemispheres is vital for creating a habitable environment. Relay stations or hubs, positioned at the terminator line, which is the area separating day and night, could serve as critical infrastructure for energy distribution and possibly as logistical bases. These hubs would take advantage of the relatively stable conditions at the terminator zone, where temperatures might be more moderate to facilitate the exchange of resources and human activity. If Proxima B lacks a natural atmosphere, biodomes would be essential for human colonization. These domes would function as controlled environments, providing breathable air, regulated temperature, and protection from radiation. Constructed from advanced materials such as graphene or transparent aluminum, these biodomes could withstand intense radiation and micrometeorite impacts. They could also be coated with reflective or absorptive materials to manage the intense light and heat on the day side or retain warmth on the night side. Inside these biodomes, closed-loop ecosystems could sustain human life. Hydroponic and aeroponic farming systems would ensure a steady food supply, while water could be recycled through advanced filtration systems. Atmospheric composition within the domes would be carefully regulated, balancing oxygen and carbon dioxide levels, potentially supplemented by artificial trees or algae bioreactors that mimic Earth's natural carbon cycle. Waste management systems would be designed to recycle all materials efficiently. There remains a slim but intriguing possibility that Proxima B might possess an atmosphere. A robust magnetic field generated by a molten metallic core could shield the planet from Proxima Centauri's intense stellar wind, preserving an atmosphere over billions of years. Additionally, if the planet has a significant mass of volatiles, such as water or carbon dioxide, or a subsurface reservoir of gases, it could potentially replenish its atmosphere despite periodic losses to space. Should Proxima B host an atmosphere, it would fundamentally alter the colonization strategy, allowing for more traditional approaches like open-air habitats and atmospheric resource utilization. The potential for colonizing Proxima B hinges on leveraging its unique conditions to sustain energy production and life support. Whether harnessing perpetual sunlight on the dayside or innovating with biodomes in a harsh, airless environment, humanity's ingenuity and adaptability would be key to transforming this distant world into a second home. This may seem like a distant dream right now, and rightfully so. However, progress is happening even right now. The search for extraterrestrial intelligence in the Proxima Centauri system. In 2021, astronomers detected a narrowband radio signal originating from the direction of Proxima Centauri. This discovery, made during the Breakthrough Listen project, a $100 million initiative dedicated to scanning the skies for intelligent life, sparked significant interest and debate. The signal, identified as BLC1 or Breakthrough Listen Candidate 1, was observed at 982 MHz, 0.002 MHz, a frequency rarely used by human technologies and devoid of natural cosmic emissions. Such a specific frequency is significant because narrowband signals are typically associated with artificial transmission rather than natural phenomena. Moreover, analysis revealed that the signal demonstrated periodic patterns. Follow-up observations have not yet replicated the signal, leaving its origin ambiguous. While it could be an artifact of human interference, such as satellite reflections or Earth-based transmissions, its directionality toward Proxima Centauri continues to intrigue researchers. While primarily attributed to the star's flares, these pulses might encode information if modulated in a deliberate pattern. Such a method would be well suited for a civilization accustomed to high radiation environments. Researchers have catalogued additional unexplained narrowband frequencies during long-term monitoring of Proxima Centauri. While no other signals have matched the precision of BLC1, this growing archive fuels speculation about ongoing extraterrestrial communication attempts. The potential origins of these signals raise profound questions about their intent and the nature of any civilization that might have sent them. Maybe an intelligent alien civilization is trying to establish contact. This may seem a bit far-fetched, but this is exactly how the biggest and brightest minds among us think. The Voyager golden records are a perfect example of this. Humankind has similarly tried to announce its presence to an alien civilization. Is anyone listening? We don't know yet, but these records were launched with great hope aboard NASA's Voyager spacecraft. Esteemed physicist Stephen Hawking even went as far as to warn us that receiving signals from extraterrestrial civilizations, if we do come across them, could pose risks, as their intentions might be unpredictable. Many theorists suggest that extraterrestrial civilizations might send simple, universally comprehensible messages, a hello in the cosmic bottle. These could include mathematical constants, such as the Fibonacci sequence or prime numbers, providing an unmistakable sign of intelligent origin. Whatever this signal was, the hope for establishing first contact remains strong. This brings us to other frontiers in space exploration. Our next move in the cosmos. What we have seen on Proxima B is not unique, in fact, far from it. The JWST has, as mentioned earlier, unveiled many habitable exoplanets that may already harbor life. While the possibilities are limitless, we have to start small. Naturally, our cosmic neighbor, Mars, has captivated us for centuries. Its geological features, evidence of ancient water, and relative proximity to Earth have made it the persistent focus of scientific endeavors. Recent missions, particularly those conducted by NASA, have revolutionized our understanding of the red planet, unveiling a world that once might have harbored conditions suitable for life and laying the groundwork for future human exploration. NASA's Mars rovers, Spirit, Opportunity, Curiosity, and Perseverance have significantly advanced our understanding of the red planet's history and habitability. Spirit and Opportunity, which landed in 2004, uncovered compelling evidence of Mars's watery past, including the discovery of hematite and clay minerals, suggesting environments once favorable for life. Curiosity, launched in 2012, furthered this exploration by identifying organic molecules, ancient riverbeds, and methane fluctuations, providing critical insights into Mars geology and potential for supporting life. Perseverance, which landed in 2021, represents the most advanced rover to date, focusing on astrobiology, sample collection, and preparations for future human missions. It has identified ancient microbial habitats and collected samples that could offer unprecedented insights into Mars' potential for life when returned to Earth in the future. Perseverance's mission is enhanced by Ingenuity, a groundbreaking helicopter that has achieved controlled, powered flight on Mars despite its thin atmosphere. Since its first flight in 2021, Ingenuity has completed over 50 flights, scouting terrain and mapping paths for Perseverance while capturing high-resolution images of the Martian surface. This innovative aerial exploration has opened new avenues for studying inaccessible regions and has set the stage for future missions. Together, these rovers and their technological advancements have reshaped our vision of Mars, paving the way for deeper exploration and the possibility of human settlement. This means that Mars, not too many years from now, can become the Jamestown of humankind in space, paving the way for our conquest of space. But why does this even matter? Why bother colonizing planets when it's expensive and also risky? Well, this brings us to the new space race. Back in the 60s and 70s, the United States and the Soviet Union battled it out, each trying to claim the space for itself. This space-age rivalry ended in 1969 when the United States successfully landed men on the Moon. That space war is all set to erupt in full might once again. And there's a new player in town: China. Their Chang'e program is a standout example of how space exploration has become a key area of focus for global superpowers. With its series of lunar missions, China has demonstrated technological prowess and ambitious aspirations. The Chang'e 3 mission in 2013 marked a significant achievement with its soft landing on the Moon and deployment of the U-2 rover to explore the lunar surface. Chang'e 4 made history in 2019 as the first mission to land on the Moon's far side. In 2020, Chang'e 5 successfully brought back lunar samples, the first such feat since the 1970s. India too has carved a unique niche in this race with its Mars orbiter mission, popularly known as Mangalyaan. Launched in 2013, this mission made India the first Asian nation to successfully reach Mars, and on its very first attempt, an accomplishment that astonished the world. What is even more remarkable is the mission's cost efficiency. It was completed with a budget of just $74 million, a fraction of what similar missions by other nations have required. Mangalyaan has contributed significantly to our understanding of Mars's atmospheric processes and surface features, including capturing detailed images of its two moons, Phobos and Deimos. The success of this mission has inspired India to plan follow-up missions with enhanced capabilities, further cementing its place in the annals of interplanetary exploration. The European Space Agency, or ESA, has also made invaluable contributions to space exploration through missions like Mars Express and Rosetta. Mars Express, which has been operational since 2003, has provided detailed studies of the Martian surface and atmosphere. It confirmed the presence of water ice at the planet's poles and discovered subsurface lakes beneath the southern ice cap, revolutionizing our understanding of Mars's potential to harbor life. Similarly, the Rosetta mission, launched in 2004, achieved the historic feat of landing a probe on a comet. By studying Comet 67P Churyumov-Gerasimenko, Rosetta offered groundbreaking insights into the early solar system and the role of comets in delivering water and organic compounds to Earth. These missions showcase Europe's critical role in advancing planetary science and inspiring global collaboration. Icy moons like Europa are also emerging as the next frontier in the search for extraterrestrial life. NASA's Europa Clipper mission, launched in October 2024, aims to conduct a detailed reconnaissance of Europa, one of Jupiter's most intriguing moons. With its subsurface ocean potentially harboring life, Europa is a prime target for astrobiological research. Equipped with high-resolution cameras, ice-penetrating radar, and spectrometers, the Europa Clipper will analyze the moon's icy crust and search for signs of life in its hidden ocean. Meanwhile, ESA's JUICE, or Jupiter Icy Moons Explorer mission, will explore Europa alongside Ganymede and Callisto. Moreover, the Mars Sample Return mission, a collaborative effort between NASA and ESA, represents one of the most ambitious undertakings in space exploration. This mission will retrieve soil and rock samples collected by the Perseverance rover and transport them back to Earth for detailed analysis. The logistical challenges of this endeavour are immense, involving advanced technologies like a Mars ascent vehicle and orbital docking. However, the potential rewards are unparalleled. The samples could reveal Mars' climate history, the presence of ancient microbial life, and the evolution of its atmosphere. The implications of this modern space race extend far beyond scientific discovery. It is a geopolitical competition. Whoever rules the space will also inevitably rule the world. But there is an exploration angle as well. Unsolved mysteries of the universe. The vast and incomprehensible universe holds mysteries that challenge even the most advanced scientific minds. Among its greatest enigmas is the elusive nature of dark matter and dark energy, two phenomena that together account for roughly 95% of the universe's total mass-energy composition. Dark matter, though invisible and undetectable by conventional means, acts as the gravitational glue holding galaxies together. Without its unseen influence, galaxies would disintegrate under their own motion. However, the exact composition of dark matter remains unknown. Dark energy, on the other hand, drives the accelerating expansion of the universe. Its mechanisms remain shrouded in mystery. The origins and ultimate fate of the universe are equally perplexing, rooted in the cosmic event known as the Big Bang. Approximately 13.8 billion years ago, the universe emerged from an unimaginably hot and dense singularity, rapidly expanding into the cosmos we observe today. Yet, questions linger about what preceded this event and whether the Big Bang was a singular occurrence or part of a cyclical process of creation and destruction. Theories about the universe's future are just as varied, ranging from eternal expansion, where galaxies drift further apart until stars burn out and matter decays, to the possibility of a big crunch, where the universe reverses its expansion and collapses back into a singularity. Another possibility is the Big Rip, driven by dark energy, where even atoms are torn apart. Galactic formation, the enigmatic nature of supermassive black holes, and the search for extraterrestrial life are also among the most profound mysteries of the cosmos. Galaxies, from spirals like the Milky Way to irregular forms, often host supermassive black holes at their cores, such as Sagittarius A. These black holes, with masses millions to billions of times that of the Sun, influence galactic evolution, yet their origins and relationship with their host galaxies remain unclear. Simultaneously, humanity's quest to discover life beyond Earth has expanded through missions to icy moons, exoplanet studies, and programs like SETI, driven by the discovery of extremophiles on Earth. While evidence remains elusive, the implications of finding life, particularly intelligent civilizations, would challenge our understanding of existence and raise profound ethical and philosophical questions. Also, Proxima B, while a hellscape from the looks of it, may hold in itself the answers to many questions about astrobiology and habitability. Overall, the mysteries of the cosmos are questions that touch on the very essence of existence. One day, we'll be wiser, and be able to answer what is today unanswerable. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.